seeing this? Is that right side up? Yes, it is. There is a topic that we have not addressed yet, and that is terminal voltage. So terminal voltage is the voltage produced by a battery if you attach a voltmeter to its terminal. And so let's say the battery is rated at like 6 volts. It's a 6-volt battery. If you actually hook up a voltmeter to that, it's not going to quite be 6 volts. It might be 5.4 or 5.9 volts. Why does it lose some of its voltage? What do you think, Chris? Sure, you betcha. There's a little bit of resistance in the battery itself. If you're, connecting the terminals using, clamps. Have you ever taken 2 9-volt batteries and plugged them together backwards, and they get really, really, really hot? You're not supposed to do that, but everybody does it. That's because you're actually pushing the chemical reaction backwards through one of the battery, and your typical, cheapo 9-volt batteries are not designed to run backwards like that. If you let it stay there long enough, you could get breach the seam on the battery, and then you might have battery acid that would ooze out. Don't do that, Chris. I can tell by the look on your face. But here's something cool you can do. Boy Scouts are taught this, and that is that, I don't know why they teach, maybe they should teach Girl Scouts this too. Anyways, take a 9-volt battery with you on a hiking trip and some steel wool, and if you actually put the steel wool in contact with a 9-volt battery, it'll spark, and it'll be a great way to start a fire. You could also take matches. But it's what? A true Boy Scout, that's right, would use have you seen the friction, like the bows that you can use to start a fire? It's a very cool, Survivor Man does it. And, Back row, shut up. Oh, milkweed.
Yeah.
Oh.
Use that on, I don't know, my neighbor, big Boy Scout, Girl Scout people and stuff. Has all grew up with them.
Yeah.
But we don't always make fires.
Yeah, if you, there's a lot of different fun ways to look up how you can start fire without a match, and that was always a fun summertime activity in our house. So terminal voltage is due to usually the internal resistance provided by a battery, okay? And it's going to make the voltage a little bit lower than what it actually says, what the rating says on the battery. In a circuit diagram, it'll look like this. It'll look like a battery, and then there'll be a resistor right next to the battery. So that really means that's the internal resistance of the battery itself, and usually there's a lowercase r there to designate that, okay? So lowercase r means the battery itself. So let's say that this was a 6-volt battery, okay? That was the rating on the battery, but we know it's not going to quite be 6 volts. And little r was 1 ohm. So that's the resistance produced by the chemicals in the battery themselves. And if this battery, we don't have the rest of the circuit hooked up, but if this battery produces a current of 0.1 amps, okay, that actually runs through the battery, 0.1 amps, what would the voltage drop by this internal resistance be if you used Ohm's law? So use V equals IR, but now it's little r. Same equation works. And by the way, if you see something like this and you're given that resistance, you just treat it like it's another series resistor. Okay?
What's in front of the A?
0.1, right there?
Yeah.
0.1 amp.
Oh,
That's what's running through the battery. So if this is actually going to be the voltage drop that we're going to calculate by the current and resistance. So the voltage drop would be 0.1 amps times 1 ohm, or 0.1 volts, right? So what would the terminal resistance of that battery be? Nope. It's going to drop 0.1 volts, so what would the terminal resistance be? 5.9. 6 volts, subtract that 0.1. Yeah, so 5.9 is the term. So V terminal would equal the rating minus the voltage drop by the battery itself, or 5.9. Okay? So that's all you have to do there. Now let's talk about different ways that you can organize batteries. So if you've ever put batteries into a flashlight or replaced the batteries in your calculator, you know that sometimes the batteries are like set up right next to each other, and sometimes, like in a flashlight, one goes in front of the other. If you look at the batteries up here, I've got a positive to a negative, and so that's actually organizing the batteries in series. Okay?
Can you read that?
Yep. So the batteries are organized in series, and if these are 4 1.5 volt batteries, and that's what you have in your calculator, voltage in series would equal 4 1.5 volt batteries. Take a guess at what the overall voltage is there. 4 times 1.5, which is how much? 6, yeah. So that would produce 6 volts. Does that make sense?
What's the circle looking thing?
At 4 batteries at 1.5 volts each. That's like my own notation. I say other people use that for at, don't they?
Yeah.
Okay.
It just looks like 2 circles.
Oh, yeah, it's squiggly. Sorry about that. All right, there's another way to do this, and that is in parallel. And if we did the same thing, okay, my bad, sorry, these are batteries, not resistors. It's 4 of them, same 4 batteries. So now if I have the voltage in parallel, and these are 4 1.5 volt batteries, again, I'll just tell you what this is. It's 1.5 volts. Because they're parallel, right? So what's the advantage? Why? First of all, there is a similar advantage to setting up your batteries in parallel, just like we set up resistors in parallel. And that would be, what if one of these 4 batteries was older than the others and it ran out of chemical reactants? So let's say we lost this battery because it's just not fresh enough anymore. So we lose this, what happens to the overall voltage?
It just goes down.
It stays the same. So what's the advantage, besides the fact that you have backups, right?
Well, if it's in series, wouldn't the internal resistance of the battery stack?
That is true, absolutely.
So you don't have that in parallel.
Yep. What's another reason to organize your batteries in parallel? Because you don't get increased voltage this way. So besides if you lose one, obviously then we're still at 1.5 volts.
If one of them dies, you're not forcing current through it, but if the rechargeable battery is forcing current through it, will destroy it.
True. What happens if one of these dies? What happens if you take one battery out of your calculator? It doesn't work. So if you lose one of these batteries, you're done. Also, another reason to set up parallel batteries is it allows them to last longer. So we were drawing the same voltage, but the current demand will be less. So let's say all 4 of these are working to produce 1.5 volts. This one will give up 1/4 of the current, this one will give up 1/4 of the current, and so on. So it actually allows your batteries to just last a little bit longer.
But you could really only use one if you wanted to.
Yeah, it would just burn up quicker, yeah. A couple of you open your calculators right now and take a look at your batteries. There are 4, yes. Those are 4 1.5 volt batteries. Are they in series or parallel?
I don't series.
I don't know.
Because if we took one out, they wouldn't work.
Okay, okay. What's going on with yours?
Two over here, two over here.
Oh, that's weird.
These are clear. These are.
Yeah, look at the positive and negative terminals and tell me if they are in series or parallel, and here's how you'll know. They're aren't your batteries all right next to one another, except for Andrew's?
Yep.
So are they, all the positive terminals on the same side and all the negative terminals on the same side?
Nope.
So it's positive, negative, positive, negative, positive, negative. What does that tell you? Series, correct. So it's actually like a serpentine if you were to look at the circuit board underneath those batteries. Another way to tell that it's in series is what happens if you take one of those 4 batteries out. It won't work. So that means it must be like this, even though it physically looks like it's kind of set up more like a parallel.
What type of thing can you take a battery out and have it still work?
Most batteries are in series in handheld type devices like this. I don't know. Chris Klusendorf was talking to me about like a launcher that he has for his rockets, and he had a battery in backwards, but I think it was still in series. We were trying to sort of debrief it verbally. I was just going to ask that. I'm not the person who replaces, but they're usually more than one battery. They're in the same direction, so that would probably be series. Aren't they one after another? This is how mine is.
It's like, they're 4 and they like choose positive, like negative, positive.
So that's series, yeah. It's negative, positive, negative, positive.
What's on top of each other?
Your remote's different?
I think all the remotes are different. Well, I mean, like,
I mean, you could figure it out. If you take out one of the batteries and it doesn't work, it's in series.
mine's back on top of each other.
So
I mean, I'm not saying different if it's series or parallel, but like, it's not like.
most battery-operated stuff is in series, but you'll know if you take it out. If you take it out and it still works, it was in parallel.
What about a flash?
Amount of voltage you can get from it.
Yes,
With a series circuit, the same set of batteries, you get 6 volts rather than 1.5.
correct. So it depends on what your needs are. Right, that's correct. Chris?
So one of my remotes, I think is for one of the TVs. It's like you put a battery in, but it like goes into the remote, and then you put the next one in, and then
So it's like a flashlight, that's in series. Especially if you have to put the batteries in the same direction. So it's like positive to negative, positive, like what Alex was just talking about. Yeah. Okay. All right. So what happens if I have multiple batteries in a circuit diagram? That's what we're going to finish with today. I know. Because you're having so much fun. Listening to me yell at the back row. Huh? I don't know. All right, let's say I have, and I'm not going to put any resistors in quite yet. Okay? A set of, it's like a parallel circuit with 2 batteries in it. And I just want to analyze the way the current will flow. So current comes out of the positive and into the negative, right? Out of the positive and into the negative. I'll call this I1 and this path I2. What do you think is going to happen at these junctions? So when I1 and I2 come together right here, what would be the most logical exit from that junction? Down and then this way? Okay. So yep, that makes sense. So that means I3 would be like this. And what would the relationship be between I1, I2, and I3 at the junction?
I1 plus I2.
Yes. I1 plus I2 equals I3. Correct? All right, now let's do this same thing, but let's put some resistors in there and actually throw some numbers around. But if this concept makes sense to you, then that's all good. When you have batteries like this in parallel, when you plug your cell phone in every night, you're actually pushing the current backwards through that battery. And it's a rechargeable, it's a reversible chemical reaction. So when you push the current backwards, you basically push the products back into being reactants, right? Used to be, I don't know if you remember this, but used to be the rechargeable batteries only had like a specific number of charges that could be reset. They're much, much better now. Usually the life of the phone is less than the life of the battery, right? Like you drop your phone long before you need a new battery. But this still works, and let me show you how we can figure out the setup. So let's say I have a 3 ohm resistor and then a couple of batteries. One of them is a 6 volt battery. I'll put a little resistor right here. and the other is a 12-volt battery. Can you see that? And we'll have our current come out of the positive into the negative. Call this one I1. Call this one I2. And just like the top example, it would make sense that I3 would run this way, right?
Couldn't it go the other way too, though?
If it went to it, yeah, except for if I3 came back this way,
Oh, yeah,
that we'd have to go backwards somewhere. Now, that's possible. Spencer's right. It is absolutely possible that maybe one of these pathways is actually backwards. Which one would be more likely to be backwards? Zach, this is what you were working on. Which one would be more likely to run backwards, the 6-volt battery or the 12-volt battery?
6 volts.
Right. So in other words, the 12-volt battery, another possibility is the 12-volt battery, the current comes here, it splits into I3, and it forces the current backwards through the lesser battery. That's what you do when you plug your cell phone in every night, is you have the big 120 volts coming out of the outlet, and your batteries are probably 6 volts or less in your cell phone, so we're just going to force that current backwards, reset the reaction. Let's do the math to figure out whether or not we were correct. So we're setting this up in a way that seems logical. Matthew?
Can you typically overcharge something?
Used to be that you could. They have safeguards in place now. But yeah, I mean, if you take two non-rechargeable 9-volt batteries and plug them in backwards, you know, the positive and negative terminals backwards, those will overheat and you'll fry those. Yeah. All right, so let's set this up. First, the junction rule. I1 plus I2 equals I3. Correct? That's at this junction right here, so I1 and I2 come together to make I3. And then let's do loop rule. So if I do just this top loop, how much voltage do I have to drop right here? So just the top loop. How much volts do I have? I start with 6 volts, and there's only one resistor, so how much voltage do I have to drop? All 6, that's the rule. You got to drop the voltage, okay? So what would the current be through this resistor if I've dropped 6 volts here? 2 amps. So I3 is 2 amps. I3 is 2 amps. I'm going to put that right there. Now let's look at, that was the top loop, now let's look at this big loop, okay? So I'm dropping 6 volts here. I have 12 volts available, so how much voltage do I have to drop right here? There's the other 6, right? So the top loop and the big loop are happy, right? And what would I2 have to be? 6 and 1, so what's the current right here? 6 amps. So I2 is 6 amps, and I1 would, what? Is that kind of where you were, Zach, in your problem? Did you end up with a negative current? Then that's correct. You did that correctly. So if I1 ends up being, what would it be to make this math work here? I1 has to be negative. I1 would be -4, right? -4 amps. So what that means is that we guessed wrong in terms of the direction right here. So if the current were flowing in the opposite direction, the math would all work out, wouldn't it? So if this is, we said I2 is 6 amps coming into this junction, right? And we said I3 is 2 amps, then I1, if it was running backwards, would be 4 amps. Does that make sense? And we guessed wrong because this battery is actually being treated like a battery that's being charged. But it's okay. You'll know if you guess the wrong direction if you end up with a negative current. So, Zach, you were probably doing that problem correctly, and negative current means you just need to swap directions for whichever one came out negative. Okay?
Can you just make it a 4?
Sure. Change this equation, put the equal sign in another spot, and it becomes a positive 4. That's right. Yeah, so instead of 1 plus 2 equals 3, it should be 2 equals I3 plus I1. Okay? All right, so tonight I have the really hard circuit problems, and they're in the back of the room. And I'm going to pull those out for you so that you can take them home. I want you to get started on that tonight. Don't take them yet, because I've got to organize them just a little bit. I want you to get started. Yeah. Started on these. Come on back. Started on these tonight. We will work on them again in class tomorrow, and then we will also take another quiz, I think, or maybe retake this quiz for you. That's that whole packet. Yep, whole packet. That's one packet. No, I'm being serious. Yeah, do about half of it tonight, and the other half tomorrow. Zach, you already have that.
You're washing that last night? Yeah. Wash it? I was like, wash it, like, okay, I can turn it off, let's do that tomorrow.
Oh, would somebody go up and push stop on that record thing? Sure. Okay. Just say something over there. Oh, wow. It is. Like my life. Hey, who's up front? Are you working on that for me, Seth? Thank you. Go up to like where it says file and down to where it says stop.